In 2015, a group of amateur astronomers discovered something that should not exist. A star, 1,400 light-years away, was dimming by over 20%. No planet could do that. No known phenomenon could explain it. Scientists had 150,000 stars to study. Only this one broke every rule. Over the next few minutes, we will chase the strangest theories ever proposed. Giant comets, dying moons, and yes, alien megastructures. If you enjoy this journey, consider liking and subscribing. Now, let us begin. In 2015, a group of volunteers were staring at graphs on their computer screens. They were not professional scientists. They were ordinary people, teachers, engineers, retired hobbyists, and they had just stumbled onto something that would shake the foundations of astronomy. These volunteers were part of a project called Planet Hunters. NASA had launched the Kepler Space Telescope 6 years earlier with one goal: find planets orbiting distant stars. The telescope did its job almost too well. It collected so much data that NASA's own team could not process it all. So they asked the public for help. Thousands of amateur astronomers signed up. Their task was simple: look at light curves. These are graphs showing how bright a star appears over time. When a planet passes in front of a star, the light dips slightly. Find the dip, find the planet. Most of the time, the work was tedious. Star after star showed predictable patterns: small dips, regular intervals, textbook transits. But then someone found a star that refused to follow the rules. The star had a name that only a database could love: KIC 8462852. It sat in the constellation Cygnus, about 1,400 light-years from Earth, and its light curve looked like a heart monitor during a panic attack. The brightness dropped, then it spiked, then it plummeted again. At one point, the star dimmed by 22%. That number might not sound impressive, but here is why it sent shockwaves through the astronomy community. When a planet the size of Jupiter passes in front of a star like this one, it blocks about 1% of the light, maybe a little more. To block 22%, you would need something impossibly large, something that, according to the laws of physics, should not exist. The volunteers flagged the data. They assumed it was a glitch. Kepler had hiccups sometimes. Instruments malfunction. Data gets corrupted. Surely this was just noise in the system. But when the project leaders checked the processing pipeline, they found nothing wrong. The data was clean. The readings were real. Dr. Tabitha Boyajian led the team investigating the anomaly. She was a postdoctoral researcher at Yale, sharp and skeptical. She did not believe in jumping to wild conclusions. But even she had to admit that this star was unlike anything Kepler had ever recorded. Out of more than 150,000 stars observed during the mission, not a single one behaved like this. The fluctuations were too large, too irregular, and there was no pattern anyone could identify. Stars do not just blink on and off like Christmas lights. Something was blocking the light, something big, something strange, and nobody had any idea what it was. Word began to spread through the scientific community. Papers were drafted, theories were proposed, but every explanation fell short. The mystery was only beginning, and what researchers discovered next made everything even more confusing. The light curve of this strange star looked like a seismograph during an earthquake: jagged, erratic, violent. Scientists had studied tens of thousands of stellar light curves before. None of them looked anything like this. Here is what normally happens when a planet crosses in front of its star. The brightness drops by a tiny amount, usually less than 1%. The dip is smooth, symmetrical, and predictable. You can set your watch by it. Planets orbit on schedules. Their transits repeat like clockwork, but this star followed no schedule. The dips came at random intervals, sometimes days apart, sometimes weeks, and the depth of each dip varied wildly. One event blocked 8% of the light. Another blocked 15%. The largest recorded event swallowed 22% of the starlight in a single plunge. To put that in perspective, Imagine standing in a parking lot under a street lamp. Now imagine something passing overhead that blocks nearly a quarter of the light reaching you. Not a bird, not a plane. Something colossal. Something that makes no sense. The Kepler telescope monitored this star almost continuously for 4 years. During that time, it recorded more than a dozen significant dimming events. Each one was different depth, different duration, different shape. Some dips lasted only a few hours, others stretched across days. A few had sharp, sudden drops followed by gradual recoveries. Others showed the opposite pattern. Scientists use words like aperiodic and asymmetric to describe behavior like this. But those clinical terms hide the real emotion in the room: confusion, frustration, and underneath it all, excitement. Because when the universe throws you something you cannot explain, it usually means you are about to learn something new. Dr. Boyajian and her team nicknamed the star after its catalogue number. But soon, the astronomy community gave it a simpler name. They called it Tabby Star. It was a small tribute to the woman who brought it to the world's attention, and it stuck. Today, even in formal scientific papers, the name Tabby Star appears. But a catchy name did not solve the mystery. The team needed answers. What kind of object could block that much light? Why was the pattern so chaotic? And why had no other star in Kepler's vast survey ever shown anything like this? The obvious explanations came first. Maybe a giant planet was responsible. Maybe a cloud of dust. Maybe a swarm of comets. Each theory sounded reasonable at first glance, but one by one, they fell apart under scrutiny. The irregularity was the killer. Natural objects follow natural laws. Orbits are ellipses. Dust clouds disperse. Comets travel in predictable arcs. Nothing in the known universe behaves the way Tabby's star was behaving. Unless something was out there that we had never encountered before, the hunt for answers was about to begin. And the first suspect on the list seemed like an easy case to close. It was not. The Kepler Space Telescope lifted off from Cape Canaveral in March of 2009. Strapped to a Delta II rocket, it carried humanity's most ambitious planet-hunting instrument into the void. Its mission sounded simple: stare at a single patch of sky, watch for blinking stars, find other worlds. The patch Kepler chose was in the constellations Cygnus and Lyra. About 150,000 stars fell within its field of view. For nearly a decade, the telescope would watch them without blinking. Every 30 minutes, it recorded the brightness of each star. The data piled up, terabytes of light curves waiting to reveal their secrets. The technique Kepler used is called transit photometry. When a planet passes between its star and Earth, it blocks a tiny fraction of the starlight. The bigger the planet, the bigger the dip. The closer the orbit, the more frequent the transits. By measuring these dips, scientists could calculate the size of distant worlds, the length of their years, and sometimes even hints about their atmospheres. Kepler was spectacularly successful. Over its lifetime, it confirmed more than 2,700 exoplanets, rocky worlds, gas giants, planets orbiting 2 stars at once, planets so close to their stars that their surfaces glow like embers. The telescope rewrote our understanding of how common planets are in the galaxy. The answer turned out to be very common. Almost every star has at least one, but success came with a price. The flood of data was overwhelming. NASA's team could not keep up. That is why they created the Planet Hunters project. Citizen scientists around the world logged in, examined light curves, and flagged anything unusual. The human eye, it turns out, is remarkably good at spotting patterns that computers miss. Most of the flagged stars turned out to be false alarms, instrumental noise, binary star systems, eclipsing pairs where 2 stars orbit each other. Interesting, but not mysterious. Then the volunteers found KIC 8462852. Out of 150,000 stars, this one was an outlier among outliers. Nothing in Kepler's entire database matched its behavior. The dips were too deep. The timing was too random. The asymmetry was too pronounced. Every standard explanation failed before it even got started. Dr. Boyajian later described her first reaction as disbelief. She assumed the data was corrupted. She ordered a full audit of the processing pipeline. Technicians checked every step, from the raw sensor readings to the final calibrated output. They found nothing wrong. The readings were accurate. The star was real, and its behavior defied every model astronomers had built over decades of observation. Kepler had found something genuinely new. Not just a new planet, not just a new phenomenon, something that did not fit any category. Now, the real work began. The team needed to rule out every natural explanation before considering anything more exotic. The first candidate seemed obvious. What if a massive planet was blocking the light? The answer came quickly. And it was not what anyone expected. The simplest explanation is usually the right one. That principle has guided science for centuries. So when astronomers first saw Tabby's star dimming by 22%, the obvious question was this: could a really big planet be responsible? The logic seemed straightforward. Kepler was designed to find planets. Planets block starlight. Maybe this star just had an unusually large one. Case closed. Move on to the next mystery. But the math destroyed that idea almost immediately. Tabby's star is roughly 50% larger than our own star. It burns hotter and brighter. When a planet passes in front of it, the amount of light blocked depends on the size ratio between the planet and the star. A planet the size of Jupiter, the largest in our solar system, would block about 1% of Tabby's light, maybe 1.5% if we are being generous. To block 22%, a planet would need to be about half the diameter of the star itself. That is not a planet. That is a small star. And here is the problem. Objects that large do not stay planets for long. There is a hard limit built into the laws of physics. When a ball of gas reaches about 13 times the mass of Jupiter, something dramatic happens. The pressure at the core becomes intense enough to fuse hydrogen atoms together. Fusion ignites. The object stops being a planet and becomes something else entirely. Astronomers call these objects brown dwarfs. They are not quite stars, because they cannot sustain full hydrogen to helium fusion like larger stars do. But they are definitely not planets either. Brown dwarfs glow. Not brightly, but enough to be visible in infrared. Earth-based telescopes can detect them across vast distances. If a brown dwarf were orbiting Tabby's star and causing those massive dips, we would see it. The infrared signature would be unmistakable. Astronomers checked. They pointed infrared telescopes at Tabby's star and searched for any sign of a companion object. They found nothing. No brown dwarf, no massive planet, no hidden partner lurking in the darkness. The giant planet theory was dead on arrival. Whatever was blocking the light, it was not a single large object in a stable orbit. The explanation had to be something else. This is where the mystery began to deepen. The easy answers were already gone. Scientists would need to get creative. They would need to consider possibilities that stretched the boundaries of known astrophysics. Some researchers started looking at dust. Others considered swarms of smaller objects. A few brave souls even whispered about artificial structures. But those conversations were still years away. For now, the team focused on the next most plausible candidate. If not a planet, then maybe a cloud. Young stars are surrounded by disks of debris, dust and gas swirling in the darkness. Could Tabby Star be hiding inside one? The investigation turned to the star's age, and what they found ruled out another seemingly obvious answer. Before moving forward, it helps to understand exactly why giant planets cannot explain Tabby's star. The answer lies deep inside the cores of massive objects, where temperatures and pressures reach unimaginable extremes. Every planet starts the same way. Dust and gas clump together in the disk surrounding a young star. Gravity pulls the material inward. The clump grows. Heat builds at the center. For small planets like Earth, this process stops when the rocky core runs out of nearby material to absorb. But gas giants work differently. Jupiter formed when a rocky core, about 10 times Earth's mass, began capturing hydrogen and helium from the surrounding disk. Gas piled onto gas. The planet swelled. Today, Jupiter contains more mass than all other planets in our solar system combined, and yet it is still just a planet. No fusion, no internal fire, just a ball of compressed gas radiating leftover heat from its formation. But what happens if you keep adding mass? The answer is fusion. Hydrogen atoms normally repel each other. Their positively charged nuclei push apart like magnets with the same pole facing. But under extreme pressure, the atoms are forced so close together that the nuclear forces take over. Protons merge. Energy releases. A chain reaction begins. This is what happens inside every star. Hydrogen becomes helium. The energy produced pushes outward, balancing the crushing weight of gravity. Stars shine because fusion gives them no choice. Brown dwarfs occupy a strange middle ground. They are too massive to remain inert planets, but too small to sustain true stellar fusion. They fuse a rare isotope called deuterium, which requires lower temperatures than regular hydrogen. This releases some energy, enough to make them glow faintly in infrared, but it is not enough to make them shine like stars. The threshold is about 13 Jupiter masses. Below that, the object remains a planet. Above it, deuterium fusion ignites. The boundary is firm. Physics allows no exceptions. This limit matters for Tabby Star because of geometry. To block 22% of a star's light, the blocking object needs a certain cross-sectional area. You can calculate exactly how big something needs to be to create a shadow of that size. The answer is enormous, far larger than any planet could ever grow before crossing the fusion threshold and becoming a brown dwarf. And brown dwarfs are visible. They radiate heat. Infrared telescopes can spot them across interstellar distances. If one were responsible for the dimming events at Tabby Star, it would have been detected immediately. Scientists checked anyway. They always check. Assumptions are dangerous in science. But the infrared observations confirmed what the math predicted. No brown dwarf, no impossible superplanet. The blocking object was something else entirely. With the planetary explanation eliminated, researchers turned to another possibility. A possibility that seemed promising at first glance, but it carried problems of its own. When planets are ruled out, dust usually enters the conversation. Space is filled with it, tiny particles of rock and ice drifting through the void. Around young stars, this dust collects into thick disks that can block significant amounts of light. These are called protoplanetary disks. They are cosmic nurseries, the raw material from which planets eventually form. Every solar system in the galaxy started this way, including ours. 4.5 billion years ago, our own star was wrapped in a swirling blanket of debris. Over millions of years, that debris clumped together. Planets emerged. The disk faded. Only scattered remnants remain today. Young stars still have their disks intact. Astronomers can see them. The dust absorbs starlight and re-emits it as heat. Infrared telescopes pick up this thermal glow like a warm fingerprint. It is one of the easiest ways to identify young stellar systems. So when Tabby's star started acting strange, dust seemed like a natural explanation. Maybe the star was younger than it appeared. Maybe a thick protoplanetary disk was blocking irregular chunks of light. Random clumps in the disk could explain the chaotic dimming pattern. But this theory collapsed almost as fast as the planet hypothesis. First, the age problem. Tabby's star is not young. Spectroscopic analysis revealed a mature F-type star roughly 1.4 times the mass of our own star and significantly hotter. Stars like this burn through their hydrogen faster than smaller stars. They live hard and die young by cosmic standards. Tabby's star has been around for several billion years. Any protoplanetary disk it once had vanished long ago. The material either formed into planets or dispersed into the interstellar medium. Second, the infrared problem. Even if the star somehow retained a debris disk, we would see evidence of it. Dust absorbs light and radiates heat. Warm dust glows in infrared. Cold dust is darker, but still detectable with sensitive instruments. Astronomers pointed every available infrared telescope at Tabby Star, space-based observatories, ground-based arrays. The search was thorough, and it found nothing. No excess infrared signal. No thermal signature of a debris disk. No hidden cocoon of dust. The star appeared clean, naked. Whatever was blocking its light was not a conventional dust cloud hugging the stellar surface. This was frustrating. Dust remained a possibility in some form, but the obvious version of the dust hypothesis was clearly wrong. Researchers would need to imagine stranger configurations. Dust in unexpected places. Dust with unusual properties. Dust behaving in ways nobody had considered before. But that investigation would come later. First, the team wanted to explore another idea, one that sounded almost plausible. What if comets were responsible? Comets are cosmic wanderers, balls of ice and rock hurtling through space on elongated orbits. When they pass close to a star, the heat vaporizes their surface. Gas and dust stream outward, forming the glowing tails that ancient humans once mistook for omens. Comets are messy. They leave debris trails millions of miles long. If a swarm of comets crossed between Tabby Star and Earth, they could theoretically block irregular amounts of light. Different comets at different distances would create different dip depths. The random timing might finally have an explanation. In 2016, Dr. Boyajian and her team published a landmark paper exploring this possibility. The title was memorable. KIC 8462852. Where's the flux? The initials spelled, "What the fuck?" Astronomers appreciated the joke. The paper laid out the comet hypothesis carefully. Imagine a nearby star, gravitationally disturbed, a distant cloud of icy bodies. Picture the Oort cloud surrounding our own solar system, but belonging to Tabby's star instead. A passing star could have scattered these frozen objects inward, millions of comets plunging toward the inner system. Their debris trails crossing our line of sight at unpredictable intervals. It sounded reasonable. Comets exist. Gravitational disturbances happen. Debris trails are real and measurable. The theory required no exotic physics, no unknown objects, just ordinary comets in extraordinary numbers. The astronomy community received the hypothesis with cautious optimism. Finally, a natural explanation that at least fit the broad strokes of the data. Peer reviewers approved. The paper was published. For a brief moment, it seemed like the mystery might be solved, but doubts lingered. The comet theory worked on paper. Whether it worked in reality was another question entirely. Critics pointed to the scale required. Blocking 22% of a star's light is not a small task. A single comet tail, even a spectacular one, blocks a negligible amount of light. You would need an unimaginable number of comets passing in front of the star nearly simultaneously to achieve dips of that magnitude. How many comets exactly? Estimates varied. Some calculations suggested hundreds of thousands. Others pushed into the millions. The debris field would need to contain more mass than several large planets combined, and it would need to maintain that density over years of observation. Was that possible? Theoretically, yes. Probable? That was harder to argue. No other star in Kepler's survey showed anything similar. If massive comet swarms were common, we should have seen evidence elsewhere. We had not. Still, the comet hypothesis held the lead position among natural explanations. It was the best available answer, not a good answer, but the best of a limited selection. Then new data arrived, and the comet theory started falling apart. Numbers have a way of exposing weak theories. The comet hypothesis sounded elegant in broad strokes, but when astronomers crunched the actual figures, the elegance dissolved. Start with the basic problem. Tabby's star is big, about 50% wider than our own star. Its surface area is more than double. To block 22% of that surface, You need a shadow covering an enormous region of space. Now consider what comets actually look like. The solid nucleus of a typical comet is small, a few miles across at most. Comet tails are more impressive, stretching millions of miles. But tails are thin, diffuse. They scatter some light but block very little. The particles in a comet tail are spread so thin that they are nearly transparent when viewed head-on. So, how many comets would you need? The estimates were staggering. To create a debris field dense enough to block 22% of Tabby's light, you would need somewhere between 300,000 and several million comets passing through the same region of space at the same time. That is not a swarm, that is an invasion, and the mass involved would be extraordinary. We are talking about material equivalent to several Earth-sized planets, all compressed into frozen debris. Could such a thing exist? Perhaps. Extreme events happen in the universe. Stars collide, galaxies merge, cosmic accidents scatter material in spectacular ways. But there was no evidence of any catastrophic event near Tabby's star. No nearby stellar collisions, no gravitational disturbances. Nothing to explain where this impossible swarm of comets might have come from. There was also a consistency problem. Kepler watched Tabby's star for 4 years. During that time, the dimming events continued at irregular intervals. If comets were responsible, they would need to keep crossing our line of sight year after year. That means the swarm could not simply be passing through. It would need to be orbiting the star in some configuration. But cometary orbits are elliptical and predictable. Over 4 years, patterns should have emerged. They did not. The randomness that made Tabby's star so strange also made the comet theory increasingly difficult to defend. Comets follow physics. Their paths are calculable. The chaos in the light curve suggested something more complex than frozen rocks on predictable trajectories. Some researchers tried to salvage the hypothesis with modifications. Maybe the comets were fragmenting. Maybe collisions were creating fresh debris clouds. Maybe the orbital dynamics were more complicated than anyone realized. But these patches felt desperate. Each modification required additional assumptions, and in science, every assumption weakens a theory. The comet hypothesis was not dead, but it was wounded, and then came the discovery that nearly killed it. The dimming events were strange enough. Sudden drops in brightness, lasting hours or days. Depths varying wildly from one event to the next. No predictable pattern. These short-term anomalies had already baffled astronomers for months. Then someone decided to look at the long-term data, and everything got worse. A researcher named Bradley Schaefer made a discovery that sent ripples through the astronomical community. He examined historical photographic plates from the Harvard College Observatory archives. These glass plates dated back to the 1800s. Astronomers had been photographing the sky for over a century, and many of those images survived in carefully preserved collections. Schaefer measured the brightness of Tabby's star across these archival plates. The records spanned from 1890 to 1989, nearly 100 years of data, and what he found was disturbing. Tabby's star was getting dimmer, not in sudden dips, gradually, slowly, relentlessly. Over the course of a century, the star's brightness had decreased by roughly 20%. This should not happen. Stars like Tabby's star are stable. They burn hydrogen in their cores at steady rates for billions of years. Their brightness does not fluctuate significantly over human timescales. A 20% dimming over 100 years is not normal stellar evolution. It is not normal anything. The finding was controversial. Some astronomers questioned the reliability of century-old photographic plates. Calibration methods varied over the decades. Equipment changed. Atmospheric conditions differed. Maybe the apparent dimming was an artifact of measurement inconsistencies rather than a real phenomenon. But then, Kepler data provided independent confirmation. During the 4 years of continuous observation, Tabby's star dimmed by about 3% overall. That rate was consistent with what the historical records suggested. The star was genuinely fading, and the decline appeared to be accelerating. This was a death blow to the comet theory. A swarm of comets might explain sudden dips. It could not explain a century of gradual dimming. Comets pass by and move on. They do not slowly accumulate in front of a star over generations. Something else was happening. Something that blocked light not just in random bursts but steadily over time. The mystery had deepened considerably. Researchers began considering more exotic possibilities. Maybe material was accumulating around the star. Maybe an orbiting structure was growing. Maybe something was feeding on the star's energy. That last idea sounded like science fiction, but soon, respected scientists would say it out loud. The alien hypothesis was about to enter the conversation. And unlike most fringe theories, this one refused to disappear. Astronomers are a cautious bunch. They prefer natural explanations backed by evidence. Wild speculation is for tabloids, not peer-reviewed journals. So when someone suggests aliens, most scientists instinctively reach for alternative hypotheses. But Tabby Star was breaking all the rules. The dimming events defied explanation. The long-term fading made no sense. Every natural theory had holes large enough to fly a starship through. And in that environment of uncertainty, a few brave researchers decided to say what others were thinking. What if this was not natural at all? Astrophysicist Jason Wright was among the first to raise the possibility publicly. In interviews and academic discussions, he pointed out that the observed behavior was exactly what you might expect from a partially constructed megastructure orbiting a distant star. The concept was not new. Physicist Freeman Dyson had proposed it back in 1960. He imagined an advanced civilization building a shell or swarm of collectors around their star. Such a structure would capture nearly all the star's energy output. It would be the ultimate power source for a species that had outgrown its home planet. Dyson called it a sphere. Later thinkers refined the concept into more realistic configurations. A solid shell would be gravitationally unstable, but a swarm of millions of individual collectors could orbit the star independently. From a distance, such a swarm might look like a star surrounded by a cloud of debris, and if the swarm was still under construction, parts of it might block irregular amounts of light. The match to Tabby's star was uncomfortably close. Irregular dimming events, no clear orbital pattern, gradual long-term fading as more collectors came online. Wright was careful to emphasize that aliens should remain a hypothesis of last resort. But he also argued that dismissing the possibility entirely would be unscientific. The media had no such reservations. Headlines exploded across the internet. Alien megastructure discovered. Scientists baffled by mysterious star. Could this be first contact? The story spread faster than any astronomical finding in recent memory. Professional astronomers winced. They knew how these stories usually ended. Strange signals turn out to be equipment glitches. Mysterious objects turn out to be natural phenomena. The history of alien claims was a history of embarrassing retractions. But Tabby's star refused to conform to familiar patterns. The data was solid, the mystery was real, and nobody could offer a better explanation. For the first time in decades, the search for extraterrestrial intelligence had a specific target, a single star that might, just might, harbor signs of advanced technology. The question now was how to test the hypothesis. And fortunately, the tools existed to try. To understand why scientists took the alien hypothesis seriously, you need to understand what they were looking for. The concept of a Dyson Sphere dates back to the mid-20th century. It represents the logical endpoint of energy harvesting for any technological civilization. Here is the basic idea. Stars produce unimaginable amounts of energy. Our own star releases about 380 septillion watts every second. That is a 3 followed by 26 zeros. Most of that energy radiates outward into empty space. Only a tiny fraction strikes the planets in orbit. We capture an even tinier fraction with our solar panels and power plants. An advanced civilization might find this wasteful. Why let all that energy escape when you could collect it? The solution is to surround the star with collectors, not a single panel or a small array, but millions of structures forming a shell around the entire star. Freeman Dyson first described this concept in a scientific paper in 1960. He was not proposing a construction project. He was describing a signature. If alien civilizations existed and reached a certain level of technological development, they would almost certainly build structures like this. And those structures would be detectable. A complete Dyson sphere would capture all of a star's visible light. From the outside, the star would seem to vanish, but the sphere would still radiate heat. You cannot destroy energy. You can only transform it. The sphere would glow in infrared, a warm shell where a star used to be. Later researchers pointed out problems with the original concept. A solid sphere surrounding a star would be gravitationally unstable. It would also require more material than exists in most solar systems. A more practical design would be a Dyson swarm. Millions of individual collectors orbiting independently. Each one captures some light. Together, they harvest a significant fraction of the star's output. A partially complete Dyson swarm would look different from a complete one. Some light would still escape through gaps in the swarm. The visible brightness would fluctuate as collectors passed between the star and distant observers. And if construction was ongoing, the overall brightness might decrease over time as more collectors came online. This description matched Tabby Star almost perfectly. Irregular dimming events, long-term fading, no clear orbital periodicity. The signature of a megastructure under construction was exactly what the data seemed to show. Of course, coincidence is not evidence. Many natural phenomena can produce similar signatures, but the match was close enough to justify serious investigation. And serious investigation was exactly what happened next. The popular image of a Dyson sphere is a solid shell encasing a star. Science fiction movies love this version. A hollow world where billions could live on the interior surface. Artificial gravity provided by rotation. An entire civilization hidden inside a stellar cocoon. The physics does not work. A solid shell would require materials stronger than anything that exists. The gravitational stresses would tear apart any known substance. And even if you could build it, the shell would be unstable. Any slight perturbation would send it drifting off-center until it collided with the star itself. Engineers who think seriously about megastructures prefer the swarm concept. Instead of one impossible shell, imagine millions of smaller structures. Each one orbits the star independently. Solar collectors, habitats, industrial platforms, power stations, anything a civilization might need. A Dyson swarm could be built gradually. You do not need to construct the whole thing at once. Start with a few thousand collectors. Add more as your manufacturing capacity grows. Over centuries or millennia, the swarm expands until it captures most of the star's output. From a distance, a partial swarm would create a distinctive signal. The star's brightness would vary as collectors passed through the line of sight. The variations would be irregular because the collectors orbit at different distances and speeds, and the overall brightness might decrease over time as the swarm grew denser. This is precisely what astronomers observed at Tabby Star. The match was striking, perhaps too striking to ignore. There were counter-arguments. A Dyson swarm would radiate waste heat. Collectors absorb light and generate power. Some of that energy inevitably converts to thermal radiation. A large swarm should produce a detectable infrared excess. Tabby Star showed no such excess. Defenders of the hypothesis had responses. Maybe the civilization used the energy so efficiently that minimal waste heat escaped. Maybe the collectors were designed to radiate in unusual wavelengths. Maybe the swarm was still too sparse to produce a measurable signal. These explanations felt stretched. Each one required additional assumptions, but they were not impossible. And as long as they were not impossible, the hypothesis remained alive. The scientific community was divided. Most astronomers bet on an undiscovered natural phenomenon. A few held out hope for something more extraordinary. There was only one way to settle the debate. Point more instruments at the star and gather more data. The search was about to intensify. Scientists prefer careful language, qualifications, caveats, statements hedged with uncertainty. The public prefers excitement, drama, clear answers to mysterious questions. When those two worlds collide, chaos follows. The alien megastructure hypothesis hit the mainstream media like a meteor. Headlines screamed about contact with extraterrestrial intelligence. Talk shows debated whether we were alone in the universe. Social media exploded with speculation, conspiracy theories, and wild misinterpretations of the actual science. Tabby Star became the most famous stellar object since the North Star. People who had never heard of Kepler suddenly knew about the strange blinking light 1,400 light-years away. Search traffic for terms like Dyson Sphere and alien megastructure broke records. The attention was both a blessing and a curse. Funding for follow-up research became easier to secure. Public interest in astronomy surged. Young people expressed new curiosity about space science. The mystery was inspiring a generation, but the coverage was also frustrating for researchers. Most headlines overstated the evidence dramatically. Some claimed scientists had confirmed alien structures when nothing of the sort had happened. Others mocked the entire investigation as wishful thinking by desperate astronomers. Dr. Boyajian found herself in an uncomfortable spotlight. She had never endorsed the alien hypothesis. Her original paper focused entirely on natural explanations. But her name was now permanently linked to the most sensational interpretation of her discovery. Interviews multiplied. Speaking requests flooded her inbox. The serious work of scientific investigation competed with the demands of public attention. Jason Wright faced similar pressures. He had raised the alien possibility as a legitimate scientific hypothesis worth testing. The media transformed that careful position into breathless certainty. Headlines quoted him, saying things he had never actually said. Corrections went unnoticed while misquotes spread virally. The astronomy community learned a painful lesson. In the age of instant global communication, nuance dies quickly. A hypothesis becomes a theory, becomes a fact within hours of publication. The careful process of scientific verification cannot compete with the speed of social media. But amid the noise, real science continued. Serious researchers designed serious experiments. If something unusual was orbiting Tabby Star, they intended to find out what it was. The most powerful tool available was a global network of telescopes, and they were about to point directly at the mystery. The search for extraterrestrial intelligence has operated for decades with limited resources and unlimited patience. Researchers scan the skies for signals that might indicate technological civilizations. Radio waves, laser pulses, anything artificial that stands out against the natural background noise of the cosmos. SETI has never found definitive evidence of alien communication, but that has not stopped them from looking. The Allen Telescope Array in Northern California continuously monitors promising targets. When Tabby Star entered the spotlight, SETI had to investigate. For 2 weeks straight, the array focused on the mysterious star. 42 radio dishes working in concert, analyzing every frequency for any hint of artificial origin. If an alien civilization was building a megastructure around Tabby Star, they might be communicating, coordinating construction, broadcasting navigation signals, generating unintentional radio interference from their technology. The search covered a wide range of frequencies: narrowband signals that might carry encoded information, broadband emissions that might indicate powerful machinery, everything from low-frequency rumbles to high-frequency chirps. The array listened with extraordinary sensitivity, and it heard nothing unusual. No artificial signals emerged from the data. Tabby Star was radio quiet. If an alien civilization existed there, they were not broadcasting in any way the Allen Telescope Array could detect. This was disappointing, but not surprising. Radio communication might be a brief phase in technological development. Human civilization has only been broadcasting for about a century. In cosmic terms, that is an eye blink. A more advanced civilization might have moved beyond radio entirely. Laser communication, quantum entanglement, technologies we have not even imagined. The negative result did not disprove the alien hypothesis. It simply failed to confirm it. The mystery remained open. SETI researchers acknowledged the ambiguity. The absence of radio signals meant nothing conclusive. It was evidence of absence, not absence of evidence. The search would need to continue with other methods. Meanwhile, other astronomers were planning a more ambitious investigation, not listening for signals, but watching the light itself. If something was orbiting Tabby Star, extended observation might reveal its nature. A crowdfunding campaign would make it possible, and the results would finally provide some answers. The lack of radio signals from Tabby Star did not discourage true believers. If anything, it made the mystery more intriguing. Advanced civilizations might have excellent reasons to stay quiet. Consider the history of radio on Earth. We began broadcasting in the early 20th century. Our signals have been leaking into space for about 100 years. Any civilization within a 100 light-year radius could theoretically detect our presence. We have been advertising ourselves to the cosmos without even trying, but this might be reckless. The universe could harbor hostile intelligences, civilizations that prey on younger species, empires that eliminate potential competitors before they become threats. Broadcasting your location to unknown listeners might be the most dangerous thing a species can do. This reasoning leads to what some researchers call the dark forest hypothesis, the idea that advanced civilizations deliberately stay silent to avoid detection. They listen but never transmit. They observe but never reveal themselves. Space seems empty because everyone is hiding. If the builders of a hypothetical megastructure at Tabby Star followed this strategy, they would produce no detectable radio emissions. Their technology might be completely silent from our perspective. The only evidence of their existence would be the physical structure itself. This was frustrating for researchers. Radio astronomy was the easiest way to detect artificial signals. Without radio emissions, investigators would need to rely on subtler clues, light curves, spectroscopic data, infrared signatures. The evidence would be indirect and harder to interpret. There was also the possibility that alien technology operated on principles we did not understand. Our search strategies assume certain things about physics and engineering, but a civilization millions of years more advanced might use methods that look like magic to us. Their communications might be undetectable not because they are hiding, but because we lack the concepts to recognize them. The silence from Tabby Star proved nothing either way. It was consistent with natural phenomena and alien megastructures alike. The mystery demanded more data. Fortunately, an unprecedented observation campaign was about to begin. Telescopes around the world would watch Tabby Star continuously for an entire year, and what they discovered would change the direction of the investigation completely. Science costs money. Telescope time is expensive. Professional observatories have waiting lists stretching years into the future. Getting enough coverage to solve the mystery of Tabby's star seemed impossible through traditional funding channels. So Dr. Boyajin tried something unconventional. She launched a Kickstarter campaign. The goal was to fund a full year of dedicated observation using a network of ground-based telescopes, amateurs and professionals working together to monitor the star continuously. The campaign went viral. More than 1,700 backers contributed over $100,000. The astronomy community was stunned. Crowd-funded science had worked on a scale nobody expected. With the money secured, the observation campaign began. Telescopes in North America, Europe, and elsewhere took shifts monitoring Tabby's star. When the star set below the horizon at one location, another observatory picked up the watch. For 12 months, human eyes and digital sensors never looked away. The campaign caught several significant dimming events, not as dramatic as the original 22% plunge, but substantial enough to study in detail. Each event was observed across multiple wavelengths: visible light, infrared, ultraviolet, The data was richer than anything previously collected, and the data revealed something crucial. During the dimming events, not all wavelengths of light decreased equally. Blue light dimmed more than red light. Short wavelengths were blocked more effectively than long wavelengths. This pattern was called wavelength-dependent dimming, and it was a game changer. Solid objects block all wavelengths equally. If an alien megastructure made of metal and composite materials was passing between us and Tabby Star, it would cast a grey shadow. The dimming would be uniform across the spectrum, but that is not what the data showed. The selective blocking of short wavelengths pointed to something else entirely, something small, something diffuse, something that scattered light rather than absorbing it completely. In other words, dust. The alien megastructure hypothesis had just suffered a serious blow. The evidence pointed toward natural particles, not artificial construction. But the mystery was far from over, because if dust was responsible, it was unlike any dust astronomers had ever encountered. The difference between blocking and scattering might seem technical, but for the investigation of Tabby Star, it changed everything. When light encounters an obstacle, different things can happen, depending on the size of the obstacle. Large, solid objects absorb light or reflect it away. The shadow they cast is dark across all colors. Think of the shadow from a building or a mountain, gray and uniform regardless of the wavelength. But tiny particles behave differently. When the particles are comparable in size to the wavelength of light, they interact selectively. Short wavelengths scatter more easily than long wavelengths. Blue light bounces away while red light passes through. This is why Earth's sky appears blue. Molecules in the atmosphere scatter short wavelength blue light in all directions. Meanwhile, longer red wavelengths travel straight through. At sunset, sunlight passes through more atmosphere, scattering away so much blue that only red and orange remain. The dimming events at Tabby Star showed a similar pattern. During each dip, blue light decreased more than red light. The ratio matched what physicists would expect from scattering by very fine particles. Dust grains, perhaps a micrometer across, smaller than a human hair, is wide. This was strong evidence against any solid structure orbiting the star. An alien megastructure built from metals or ceramics would block light uniformly. The wavelength dependence ruled out that possibility. Whatever was dimming Tabby's star, it was almost certainly composed of tiny particles. But this raised new questions. If dust was responsible, where was it coming from? And why could astronomers not detect its infrared signature? Normal circumstellar dust is warm. It absorbs starlight and re-emits the energy as heat. Infrared telescopes should see this thermal glow clearly. But Tabby's star showed no excess infrared emission. The dust, if it existed, was either extremely cold or extremely unusual. Cold dust would need to be far from the star. But dust far from the star could not block enough light to cause 22% dips. The geometry did not work. Researchers began considering more exotic configurations. Dust spread over enormous volumes. Dust with unusual optical properties. Dust generated by processes nobody had considered. The investigation had eliminated aliens, but it had not solved the mystery. Something was producing trillions of tiny particles around Tabby's star. Finding out what would require even more creative thinking. The wavelength data delivered a verdict. Whatever was blocking light from Tabby's star, it was not solid, not metal, not rock, not any kind of constructed material that an alien civilization might use to build a megastructure. This conclusion rested on basic physics. Solid objects interact with light in predictable ways. When photons strike a solid surface, they either absorb into the material or bounce away. The process does not depend on wavelength in any significant way. A sheet of steel blocks blue light and red light equally. So does a chunk of asteroid. So does a spacecraft hull. If an alien Dyson swarm surrounded Tabby's star, it would be made of solid components. Solar collectors require rigid surfaces to focus light. Habitats need walls to contain atmosphere. Industrial platforms need structural integrity. Whatever materials an advanced civilization might use, those materials would cast uniform shadows. But the dimming events showed the opposite. Blue light dimmed significantly more than red. The ratio was consistent across multiple events observed during the year-long campaign. This was not a measurement error or a statistical fluke. It was a repeatable, verifiable pattern. The only explanation was scattering by small particles. Dust grains interact with light differently than solid surfaces. When a photon encounters a particle similar in size to its wavelength, the interaction becomes selective. Shorter wavelengths scatter more readily, longer wavelengths slip past. The math pointed to particles roughly 1 micrometer in diameter, grains so small that trillions of them could fit in a single teaspoon. These tiny specks were somehow blocking a significant fraction of light from a star 1400 light-years away. For anyone hoping for first contact, this was devastating news. The alien megastructure hypothesis had been exciting precisely because it seemed to fit the data so well. Irregular dimming, long-term fading, no clear orbital pattern, all consistent with a partially constructed swarm of collectors. But wavelength dependence broke the spell. Dust was mundane. Dust was ordinary. Dust did not require intelligence or technology or civilizations spanning millennia. Dust just required physical processes, operating on small particles. The media coverage shifted accordingly. Headlines that once screamed about aliens now focused on the disappointment. Scientists rule out alien megastructure. Mystery star explained by dust. The excitement faded as quickly as it had arrived. But researchers knew the story was not over. Ruling out aliens did not mean solving the mystery. Dust might be ordinary in concept, but this particular dust was behaving in extraordinary ways. Where was it coming from? Why was there so much of it? And why could nobody detect it through any method other than its shadow? The investigation had eliminated one hypothesis. Now it needed to build a new one from scratch. Dust explained the wavelength data, but calling the answer dust was like calling the ocean water. Technically true, but missing the point entirely. The question was not whether particles were responsible. The question was what kind of particles, where they came from, and why they behaved so strangely. Start with the scale. To block 22% of light from a star, you need an enormous quantity of material spread across a vast area. We are not talking about a cloud you could see from a spacecraft window. We are talking about a diffuse haze extending millions of miles in every direction. Trillions upon trillions of individual grains drifting through space. Each grain is tiny, about 1 micrometer across, smaller than bacteria, invisible to the naked eye, even if you held one in your hand. But collectively, these microscopic specks can cast shadows across interstellar distances. The composition remained uncertain. Silicate minerals were one possibility. Carbon compounds were another. Ice crystals coated in organic molecules. The candidates were numerous, and the data could not distinguish between them. All that mattered for the dimming events was size and quantity. The chemistry was secondary. What struck researchers as remarkable was the irregularity. If dust surrounded Tabby Star in a uniform shell, the dimming would be constant. The star would simply appear fainter than expected at all times. But the dimming came in bursts. Deep dips, lasting hours or days, then returning to normal brightness. This implied structure within the dust. Clumps and voids, dense regions and empty gaps. The distribution was patchy, not smooth. As the star rotated and the dust orbited, different configurations passed through our line of sight. Sometimes we looked through thick concentrations. Sometimes we looked through nearly empty space. The patchiness helped explain the chaos in the light curve. Random-looking dips could result from random-looking structure. No two passages through the dust cloud would be identical. The apparent disorder was actually a consequence of complex three-dimensional geometry. But this raised another puzzle. Dust clouds do not stay patchy forever. Gravity pulls clumps together. Radiation pressure pushes particles outward. Collisions redistribute material. Over time, any dust distribution should smooth out into something more uniform. The fact that Tabby's star showed such dramatic variability suggested the dust was being actively replenished. Something was generating new particles continuously. The source had to be powerful enough to maintain irregular structure against the forces trying to erase it. Finding that source became the next priority, and the candidates were stranger than anyone expected. One problem haunted every dust hypothesis: the infrared silence. Dust absorbs starlight and converts it to heat. Warm dust glows in infrared wavelengths. Telescopes designed to see heat should detect circumstellar dust easily. But Tabby's star showed no excess infrared emission. None. The star looked perfectly normal at longer wavelengths. Whatever dust existed around it was either absent or invisible to thermal detection. This was a serious constraint. It ruled out the most obvious configurations. A thick disk of debris close to the star would be warm. Temperatures would reach hundreds of degrees. The infrared signature would be unmistakable. Such a disk clearly did not exist. What about cold dust? Material far from the star would receive less radiation. It would stay cooler. Cool enough, perhaps, to avoid detection. The problem was geometry. Dust far from the star would subtend a small angle from our perspective. To block significant light, it would need to cover a huge physical area. The mass requirements became absurd. You would need planetary amounts of material spread across astronomical distances. Some researchers proposed a middle ground: dust at intermediate distances that was cold enough to avoid infrared detection but close enough to create measurable dimming. The balance was delicate. The particle sizes would need to be precisely tuned. The distribution would need to be exactly right. It sounded contrived. Too many coincidences stacked on top of each other. But nature sometimes produces contrived-looking results through perfectly natural processes. The universe is under no obligation to make sense to human intuition. Another possibility was that the dust had unusual optical properties. Most astronomical dust models assume certain compositions and structures, but real dust grains can be complex. Fluffy aggregates rather than solid spheres, coatings that change how they interact with light, materials that absorb some wavelengths while reflecting others. Exotic dust might absorb visible light efficiently while radiating heat at wavelengths our instruments could not easily detect. The infrared signature would be shifted or suppressed. The dust would hide in plain sight. Testing these ideas required detailed modeling, computer simulations of light interacting with various particle types, comparisons between predicted signatures and observed data. The work was painstaking and slow. Meanwhile, theorists were developing scenarios that could explain where all this mysterious dust might come from. The leading candidate involved violence on a cosmic scale. In 2019, a scientific paper proposed an elegant solution. The dust around Tabby's star might be coming from a moon, not an ordinary moon in a stable orbit. A stolen moon being slowly destroyed by its captor. The scenario began with a planet on a highly elliptical orbit. Most planets travel around their stars in nearly circular paths, but gravitational interactions can stretch orbits into elongated ovals. A planet on such an orbit would swing close to its star at one end and far away at the other. During a close approach, something dramatic could happen. The star's gravity would pull harder on the near side of the planet than the far side. This difference creates tidal forces. For a planet passing too close, those forces could be catastrophic. The technical term is tidal disruption. The star literally tears the planet apart. Material streams away in long filaments. The planet ceases to exist as a coherent body. What remains is a cloud of debris spreading along the original orbit. But planets rarely travel alone. Most have moons. When a planet gets tidally disrupted, its moons face uncertain fates. Some might escape into independent orbits around the star. Others might fall inward and be destroyed themselves. A few might end up in stable but extremely close orbits. The paper proposed that exactly this had happened at Tabby Star. A planet ventured too close and was destroyed. One of its moons survived, but ended up in a tight orbit, grazing the stellar surface. At that distance, the heat would be intense. The moon would slowly evaporate. Surface material would vaporize and stream away. A constant supply of fresh dust would pour into space. This explained several puzzles at once. The irregular dimming came from clumpy debris trailing behind the evaporating moon. The long-term fading resulted from dust accumulating over time. The lack of periodicity made sense because the debris spread along a complex three-dimensional structure rather than a simple ring. Computer models supported the hypothesis. Simulations showed that a disrupted planetary system could produce exactly the kind of light curve observed at Tabby's star. The numbers worked, the physics was sound, but one nagging problem remained. The same problem that plagued every other theory. Where was the infrared signature? The kidnapped moon hypothesis had a hidden bonus. It might explain not just the short-term dips, but also the century-long dimming that had baffled researchers from the beginning. Think about what happens when a star devours a planet. The tidal disruption event releases enormous energy. Material falling into the star heats up dramatically. For a brief period, perhaps years or decades, the star would appear brighter than normal. Extra fuel means extra output. But the feast eventually ends. The debris gets absorbed. The star settles back toward its baseline luminosity. From our perspective, this settling would look like gradual dimming, the star returning to normal after an unusual meal. Historical records showed Tabby's star dimming by roughly 20% over a century. If a planetary disruption occurred sometime before human observations began, the timeline could fit. We might be witnessing the aftermath of cosmic violence that happened generations ago. The evaporating moon would then explain the ongoing variability. Short-term dips superimposed on long-term fading. Two phenomena with a single underlying cause. The elegance was appealing. Researchers ran the numbers. A planet several times Earth's mass disrupted and consumed over decades. A surviving moon gradually boiling away in the stellar heat. Debris spreading through the inner system. The model predicted light curves that matched observations reasonably well. But reasonably well is not the same as perfectly. Discrepancies remained. Some dimming events had shapes the model struggled to reproduce. The exact timing of features did not always align with predictions, and the infrared problem stubbornly refused to disappear. An evaporating moon should produce warm dust. Material streaming off the surface would initially be hot. It would radiate strongly at infrared wavelengths before cooling and dispersing. The thermal signature should be detectable, yet observations showed nothing. No infrared excess, no warm glow, just the normal output of an ordinary F-type star. Theorists proposed modifications. Maybe the evaporation was slower than expected. Maybe the dust cooled quickly. Maybe the viewing geometry hid the thermal emission. Each modification required additional assumptions. The theory grew more complicated without becoming more convincing. The kidnapped moon remained a leading hypothesis, but it was far from proven. Every theory about Tabby's star eventually crashed into the same wall. The infrared silence, no matter how clever the explanation, no matter how well it fit the visible light data, the lack of thermal emission undermined confidence. Consider the basic physics. Dust absorbs starlight. The energy has to go somewhere. Conservation of energy is not optional. Absorbed photons heat the dust grains. Hot grains radiate at wavelengths determined by their temperature. This is blackbody radiation. It happens to every object in the universe. For dust near a star like Tabby's, equilibrium temperatures would range from hundreds to thousands of degrees depending on distance. Such temperatures produce strong emission in the mid-infrared. Telescopes like Spitzer and WISE were designed specifically to detect this kind of radiation. They had observed countless dusty stellar systems throughout the galaxy. At Tabby's star, they found nothing unusual. The infrared output matched a bare star with no surrounding material. If dust existed, it was somehow evading thermal detection. Several explanations were proposed. None were fully satisfying. Maybe the dust was extremely far from the star. At large distances, particles would stay cold. Their thermal emission would shift to longer wavelengths, potentially beyond the range of current instruments. But distant dust could not easily explain the deep dimming events. The geometry did not favor it. Maybe the dust had unusual composition. Certain materials might absorb visible light while remaining poor infrared emitters. The physics was possible, but required fine-tuning. Natural processes rarely produce such precisely optimized particles. Maybe the dust distribution was so diffuse that thermal emission was spread below detection thresholds. Individually cold particles contributing tiny amounts of radiation that collectively stayed invisible. This required enormous total mass spread over vast volumes. Each explanation felt like special pleading. Scientists prefer theories that make predictions without requiring excuses for every observation that does not quite fit. The infrared mystery kept Tabby Star in the spotlight. A solved puzzle would have faded from attention. An unsolved puzzle kept drawing researchers back. Every new instrument, every improved technique, every fresh dataset brought renewed hope that someone might finally crack the code. The answer remained elusive, but new possibilities kept emerging. Most explanations assumed the dust was near Tabby's star, orbiting the star, generated by processes in the stellar system, interacting with the star's gravity and radiation. But what if that assumption was wrong? Space between stars is not empty. Thin clouds of gas and dust drift through the galaxy. Most are too sparse to notice, but occasionally, a denser region might lie along our line of sight to a distant object. Light passing through such a region would be affected. The idea was simple. What if the dimming of Tabby's star had nothing to do with the star itself? What if an intervening cloud of interstellar dust was responsible? This hypothesis had attractive features. Interstellar dust is cold, very cold. Temperatures just a few degrees above absolute zero. Such cold material would produce almost no detectable infrared emission. The thermal silence would be explained automatically. The irregular dimming could result from structure within the cloud. Interstellar clouds are not uniform. They contain filaments and clumps, dense knots and empty voids. As our line of sight passed through different regions, the amount of blocking would vary. The long-term fading might indicate motion. Perhaps the cloud was drifting across our view of the star. Each year, we looked through a slightly denser region. The gradual accumulation of obscuring material would dim the star steadily over time. It was an elegant alternative, external cause rather than internal mystery. No need for exotic processes at the star itself. But problems emerged quickly. If an interstellar cloud was blocking Tabby's star, it should also affect nearby stars. The cloud would not target a single point in the sky. It would cover a region. Other stars in that region should show similar dimming patterns. Astronomers checked. Stars near Tabby's star showed no unusual behavior. Their light curves were normal. Whatever affected Tabby's star was not affecting its neighbors. There was also the timing question. Analysis of the dimming events suggested a possible periodicity, a rough cycle of about 4 years. Interstellar clouds would not produce periodic signals. They would drift steadily without repeating patterns. The interstellar hypothesis lost support. The dust almost certainly belonged to the Tabby's star system. The mystery remained local. For years, the dimming events seemed random. No pattern, no periodicity, just chaos in the light curve. This randomness was part of what made Tabby's star so strange. Natural phenomena usually repeat. Orbits cycle, rotations recur. The universe runs on rhythms. But as observations accumulated over longer time spans, something subtle began to emerge. The chaos was not entirely chaotic. Buried in the noise was a faint signal, a hint of periodicity hiding in plain sight. The suggested cycle was roughly 4 years and 4 months. Not precise, not clean, but present in the data if you looked carefully enough. Major dimming events seem to cluster around certain times. The gaps between clusters approximated this period. If real, the periodicity changed everything. A 4-year cycle suggested orbital dynamics, something circling Tabby Star at a specific distance, something whose position relative to Earth repeated on a regular schedule. The discovery supported hypotheses involving material bound to the star, an evaporating moon on a particular orbit, a debris cloud following a disrupted planet, a ring of dust with density variations. Any of these could produce periodic signals. The periodicity also argued against the interstellar cloud hypothesis. Clouds drifting through space would not repeat. They would create one-time events, not recurring patterns. The fact that dimming events clustered around a 4-year cycle pointed strongly towards something orbiting the star, but the period was long. 4 years of observation barely covered one cycle. Confirming the pattern required more data. Researchers needed to watch through multiple cycles to verify that the repetition was real and not a statistical artifact. This meant patience, more years of observation, more telescope time, more careful analysis. The mystery would not be solved quickly. Some astronomers expressed frustration. Tabby Star had been in the spotlight for nearly a decade. Public interest had waned. Funding was harder to secure. The puzzle that once captivated millions now felt like old news. But science does not operate on media timelines. Understanding the universe requires persistence. Tabby Star would keep its secrets until researchers accumulated enough data to pry them loose. The wait continues. A decade has passed since amateur astronomers first noticed something strange about a star in Cygnus. In that time, Tabby's star has been scrutinized more intensely than almost any other stellar object in the galaxy. Thousands of hours of telescope time, dozens of scientific papers, millions of dollars in research funding, and still, the mystery endures. Here is what we know for certain. Something is blocking light from Tabby's star. The blocking is irregular and unpredictable. It affects short wavelengths more than long wavelengths. This wavelength dependence points to small particles rather than solid objects. Dust, not megastructures. The dust appears to be extremely fine, grains roughly 1 micrometer across. The distribution is patchy, creating variable dimming as different regions pass through our line of sight. A possible 4-year periodicity suggests orbital dynamics, though confirmation requires more observation. The long-term dimming is real. Historical records and modern data both show the star fading over decades. This implies ongoing processes that add obscuring material faster than it disperses. What we do not know is equally important. We do not know where the dust comes from. The evaporating moon hypothesis is plausible but unproven. The devoured planet scenario fits some data but not all. Alternative explanations remain viable. We do not know why the infrared signature is absent. Every model predicts thermal emission that observations do not detect. This discrepancy suggests something about the dust that current theories do not capture, and we cannot completely rule out artificial origins. The wavelength data argues against conventional megastructures, but a sufficiently advanced civilization might build things we cannot imagine. Dust-sized machines, nanoscale collectors, technologies that mimic natural particles while serving engineered purposes. This last possibility is slim. Natural explanations deserve priority. Extraordinary claims require extraordinary evidence. But as long as significant mysteries remain, the door stays open a crack. Tabby's star reminds us that the universe still holds surprises. A single anomalous object among hundreds of thousands. A puzzle that resists easy answers. A challenge to our assumptions about what is normal and what is possible. The observations continue. New telescopes come online. Better instruments gather better data. Someday, perhaps soon, someone will piece together the final clues. The mystery will dissolve into understanding. Until then, Tabby's star keeps blinking in the darkness, 1,400 light-years away, still strange, still unexplained, still waiting for us to figure it out. The most powerful space telescope ever built now orbits a point nearly 1 million miles from Earth. The James Webb Space Telescope launched in late 2021 after decades of delays and budget overruns. Its golden mirror stretches 21 feet across. Its instruments can detect heat signatures from objects billions of light-years away, and it might finally crack the mystery of Tabby's star. Webb sees the universe in infrared. This is precisely the wavelength range where previous observations found nothing unusual around Tabby's star. The absence of infrared excess has puzzled researchers for years. Every dust hypothesis predicts thermal emission. Every observation comes up empty. But Webb operates on a different level than its predecessors. Its sensitivity exceeds earlier infrared telescopes by orders of magnitude. What looked like empty space to Spitzer might reveal faint structures to Webb. Thermal signatures, too weak for older instruments, could emerge clearly in Webb's detectors. There is another advantage. Webb can perform spectroscopy with unprecedented precision. This means breaking light into its component wavelengths and analyzing each one separately. Different materials leave different fingerprints in spectra. Carbon dust looks different from silicate dust. Ice crystals look different from rocky fragments. If researchers point Webb at Tabby's star during a dimming event, they might finally identify what the dust is made of. Composition clues could reveal origin. Knowing the material might tell us where it came from and how it got there. The telescope's schedule is packed. Thousands of proposals compete for limited observation time. Tabby's star is no longer the sensation it once was. Other mysteries demand attention, but the star remains on lists of potential targets. Its puzzle is too significant to ignore forever. Some astronomers have already submitted proposals. They want to catch the next major dimming event with Webb's instruments trained on the star. Timing is tricky. Dimming events are unpredictable, but the potential payoff justifies the effort. There is also hope for direct imaging. Webb can resolve details that blur into smears through other telescopes. If structures exist around Tabby's star, large debris clouds or asymmetric dust distributions, Webb might actually see them. Not as points of light, but as extended features with shape and dimension. This would transform the investigation. Instead of inferring properties from light curves, researchers could observe the obscuring material directly. Geometry would become visible. Models could be tested against images rather than indirect measurements. The technology exists. The capability is real. What remains is opportunity and priority. Tabby's star must compete with black holes and exoplanets and distant galaxies for the telescope's attention. But mysteries, this persistent, have a way of rising to the top. Unsolved puzzles nag at scientists. The questions that resist answers become the questions worth answering most. Webb may provide the breakthrough, or it may deepen the mystery further. Either outcome advances understanding. The universe rarely gives up its secrets easily, but we have never had better tools to pry them loose. Tabby's star is not alone anymore. In the years since its discovery, astronomers have found other stellar oddballs that defy easy explanation. The universe, it turns out, is full of things that break the rules. One example emerged from data collected by the Transiting Exoplanet Survey satellite. Launched in 2018, this telescope scans the entire sky for planetary transits. It has found thousands of exoplanet candidates, but it has also found stars that behave strangely. A star designated TIC 400 million showed dimming events eerily similar to Tabby's star. Deep irregular dips, no clear periodicity. Wavelength-dependent blocking, suggesting dust rather than solid objects. The parallels were striking. Researchers analyzed the new target with lessons learned from Tabby's star. They checked for infrared excess immediately. They searched for periodicity from the start. They applied models developed over years of studying the original mystery. Some patterns matched, others diverged. Each strange star is strange in its own way. But the existence of multiple anomalies suggests that whatever causes these phenomena is not unique. The process, whatever it is, happens more than once. This is actually encouraging. A single anomaly might be a fluke. Multiple anomalies point toward an underlying mechanism. If researchers can identify what these strange stars have in common, they might understand what makes them different from normal stars. The search has expanded. Algorithms now scan massive datasets looking for tabby-like behavior. Machine learning models trained on the original light curve hunt for similar patterns among millions of targets. The net has grown wider. Each new discovery adds constraints. If a theory explains Tabby Star but fails for other anomalies, the theory needs revision. If a theory explains all the strange stars simultaneously, confidence increases. The scientific method works through accumulation, more data, better models, gradual convergence toward truth. Some astronomers now speak of a category rather than an individual, Tabby-type stars, objects characterized by deep irregular dimming, wavelength-dependent extinction, and mysterious origins. The category is small but growing. This reframing matters. Studying a category is different from studying a single object. Patterns emerge across samples. Statistical tools become applicable. The investigation transforms from detective work into systematic science. Tabby Star blazed the trail. It drew attention and funding and curiosity, but its greatest contribution might be opening a new field of inquiry, the study of anomalous stellar dimming as a phenomenon in its own right. Other strange stars wait in the data. Some have already been found. Others remain hidden, waiting for the right algorithm to notice them. The universe keeps surprising us, and we keep learning to look. Tabby Star became famous because of aliens. Not because aliens were found, but because the possibility was taken seriously. For a brief moment, mainstream science entertained the idea that we might have detected an extraterrestrial megastructure. The hypothesis failed, but the episode taught valuable lessons. First, it demonstrated that searching for technosignatures is scientifically legitimate. Technosignatures are evidence of technology rather than biology. Artificial structures, engineered signals, industrial pollution in alien atmospheres. For decades, this kind of search was dismissed as fringe speculation. Tabby Star changed the conversation. Respected astronomers published papers discussing alien megastructures without embarrassment. SETI received serious coverage rather than mockery. Funding agencies began considering technosignature research as a valid use of resources. The taboo weakened. Second, the episode illustrated how to approach extraordinary claims responsibly. The scientific community did not leap to conclusions. Researchers systematically eliminated natural explanations before entertaining artificial ones. When wavelength data ruled out solid structures, the alien hypothesis was abandoned without defensiveness. This is how science should work. Third, Tabby Star revealed gaps in our imagination. The Dyson Sphere concept dates from 1960. For over half a century, it dominated discussions of what alien megastructures might look like. But the universe might contain technologies we have not conceived, structures that look nothing like spheres or swarms, signatures we do not recognize as artificial. The dust around Tabby Star is almost certainly natural. But what if it were not? What if an advanced civilization built machines the size of bacteria? Trillions of nanoscale devices performing tasks we cannot guess. From our perspective, they would look exactly like dust. We would never know the difference. This is humbling. Our search strategies assume certain things about alien technology. We look for radio signals because we use radio. We imagine megastructures because we understand engineering on large scales. But a civilization millions of years older might operate on principles beyond our comprehension. Fourth, the investigation showed the value of open data and citizen science. Amateur astronomers made the initial discovery. Crowdfunding financed crucial observations. The scientific process benefited from broad participation rather than narrow expertise. Future searches for alien life should embrace this model. More eyes on more data, more minds considering more possibilities. The discovery that changes everything might come from an unexpected direction. Tabby Star did not deliver aliens, but it prepared us for the day when something might. The protocols developed, the attitudes adjusted, the conversations normalized. All of this matters. When the real signal arrives, we will be readier because of a strange blinking star 1400 light-years away. Science is done by people. Behind every discovery are individuals with personalities and struggles and moments of doubt. The story of Tabby Star is also the story of the humans who unraveled it. Dr. Tabetha Boyajian was a postdoctoral researcher at Yale when the anomaly landed on her desk. She was not famous. She was not leading a major project. She was doing the unglamorous work that young scientists do, analyzing data and writing papers that few people would read. The strange light curve could have been ignored, passed over as a glitch, filed away as an unsolved oddity. Many anomalies suffer that fate. Researchers are busy. Priorities compete. Strange data gets forgotten, but Boyajian did not let it go. She organized a team. She pursued funding. She coordinated observations across continents. Her persistence transformed a curiosity into a phenomenon. The pressure was intense. Media attention exploded beyond anything she had experienced. Journalists wanted sound bites. Audiences wanted answers. The careful qualifications of scientific language got lost in translation. Headlines screamed certainty where only uncertainty existed. Boyajian navigated this storm with remarkable grace. She corrected misunderstandings without alienating supporters. She maintained scientific rigor while engaging public curiosity. She became a role model for science communication under pressure. The citizen scientists who made the initial discovery had their own journeys. People with day jobs and families and ordinary lives who spent evenings staring at graphs because they loved the stars. Their contribution was credited in the original paper. Their names appeared alongside professional astronomers in scientific literature. This matters. Science often feels like an exclusive club. Credentials required, degrees demanded, outsiders unwelcome. Tabby Star broke that barrier. It showed that curious minds with access to data can make discoveries that change how we see the universe. The Kickstarter backers were part of the story too. Ordinary people contributing $10 or $20 or $50 to fund telescope time. Their collective investment made the crucial wavelength observations possible. Crowd-funded science seemed like a novelty then. It may become standard practice. Behind every data point is a human moment. Someone deciding to look closer. Someone refusing to dismiss the strange. Someone choosing persistence over convenience. Tabby Star is named after a person for good reason. The mystery belongs to the universe, but the discovery belongs to the humans who noticed it. Science advances by eliminating possibilities. Each ruled-out hypothesis narrows the field. Eventually, only truth remains. But this process assumes we have imagined all the possibilities in the first place. What if we have not? The history of astronomy is littered with surprises. Phenomena that nobody predicted. Objects that violated assumptions. Discoveries that forced textbooks to be rewritten. Tabby Star might belong to this category. Consider what we thought we knew. Stars are well understood. Their life cycles, their internal processes, their observable properties. Centuries of study have built detailed models. These models work extraordinarily well for ordinary stars. But Tabby's star is not ordinary. It sits at the edge of the models, the place where confident predictions become uncertain extrapolations. Maybe something happens at that edge that we have not anticipated. One possibility involves magnetic fields. Stars have complex magnetic structures that evolve over time. Magnetic activity can affect surface brightness in subtle ways. Most models treat magnetic effects as minor perturbations. What if they are more significant than assumed? Another possibility involves companions we cannot see. Binary star systems are common, but some companions are dark, brown dwarfs, too cool to detect, rogue planets captured into orbit, exotic objects like primordial black holes. Any of these might interact with Tabby Star in ways that produce unusual light curves. A third possibility involves the interstellar medium in ways we have not fully explored. The space between stars contains more than just drifting dust, magnetic fields, plasma filaments, structures on scales we are only beginning to map. Light traveling 1400 light-years passes through a lot of space. What happens along the way might matter more than we think. These ideas are speculative. None has strong support from current data, but speculation is how science expands its horizons. Someone has to imagine the unlikely before anyone can test it. The danger is premature closure, deciding that dust explains everything and moving on. The comfort of an answer replacing the discomfort of a mystery. This would be a mistake. Tabby Star has taught humility. The universe is stranger than we expected. Our models are incomplete. The next breakthrough might come from an idea that seems absurd today. Keeping minds open is not the same as believing everything. It means staying curious, continuing to question, refusing to let familiarity breed complacency. The explanation we need might be one we have not imagined yet. A single strange star might seem like a minor curiosity, one object among billions, a footnote in the grand catalogue of the cosmos. But Tabby Star has implications that extend far beyond its own mystery. For astronomy, it demonstrated the value of anomaly hunting. Most research focuses on typical objects, stars that behave as expected, galaxies that follow patterns, the normal cases that test and refine existing theories. Anomalies are often dismissed as distractions. Tabby Star reversed this thinking. The anomaly became the attraction. Researchers who studied the weird star gained visibility and funding. A new appreciation emerged for objects that break the rules. The outliers might teach us more than the averages. This shift matters for how resources are allocated. Telescope time is precious. Proposals compete fiercely. Traditionally, safe projects won over risky ones. Studying well-understood phenomena was easier to justify than chasing mysteries that might never be solved. But mysteries generate excitement. Public interest follows strange discoveries more than routine confirmations. Funding agencies notice when headlines mention their telescopes. The success of the Tabby Star investigation created incentives for pursuing other anomalies. For SETI, the implications were even more significant. The search for extraterrestrial intelligence had operated for decades on the margins of respectability. Radio telescopes scanning for signals, algorithms hunting for patterns, work that many mainstream astronomers considered quixotic at best. Tabby's Star brought SETI into the conversation. Serious scientists discussed alien megastructures in serious journals. The hypothesis was ultimately rejected, but it was rejected through evidence rather than ridicule. This represented progress. The concept of technosignatures gained traction. NASA began funding research into detecting artificial signals and structures. Academic programs incorporated SETI into their curricula. The search for alien technology became a legitimate scientific pursuit rather than a fringe obsession. There is also a philosophical dimension. Tabby's Star forced people to confront the possibility that we are not alone. For a few months, that possibility felt tangible, specific, located in space and time. Not an abstract question, but a concrete investigation. Even though the alien hypothesis failed, the experience changed perspectives. The universe became a place where such discoveries might happen, where the next strange signal might be the one that changes everything. Tabby's Star expanded horizons. Scientific, institutional, imaginative. Its legacy extends far beyond whatever is actually orbiting that distant sun. 1400 light-years away, a star keeps blinking. We have watched it for a decade. We have thrown our best instruments and brightest minds at the puzzle, and still, we do not fully understand what we are seeing. This should not be discouraging. It should be inspiring. The universe is vast beyond comprehension. Our knowledge, however impressive, barely scratches the surface. Every answer reveals new questions. Every solved mystery opens doors to deeper ones. Tabby Star reminds us that wonder is not obsolete. In an age of information overload, when answers seem available for every question, genuine mysteries still exist. Things we cannot explain. Phenomena that humble our theories. The unknown has not been conquered. Humanity has been looking at the stars for thousands of years. We mapped constellations. We tracked planets. We built telescopes and spacecraft and sent probes to distant worlds. Each generation learned more than the last. The pace of discovery accelerates constantly, and yet mysteries remain, not because we are ignorant, but because the universe is infinite. There will always be more to learn, more to explore, more to wonder about. This is not a limitation, it is a gift. Tabby Star also reminds us that discovery is collaborative. Amateur astronomers made the initial find. Professional scientists conducted the analysis. Crowdfunding supported the observations. Millions of people followed the story and cared about the outcome. The investigation belonged to humanity, not just to specialists. This model points toward the future. Science increasingly operates as a global enterprise. Data flows freely, ideas cross borders, discoveries emerge from networks rather than individuals. The next great breakthrough might come from anywhere, and breakthroughs will come. Tabby's star may be solved next year or next decade. The James Webb Telescope might capture the crucial image. A clever theorist might propose the explanation that finally fits, or the mystery might persist, challenging future generations to keep trying. Either way, the search matters. The effort to understand is itself meaningful. Even when answers elude us, the pursuit expands our minds and connects us to something larger than ourselves. 1,400 light-years away, a star blinks in the darkness. We are watching, we are wondering, and we will keep looking until we understand.